Good morning, friends. We'll start Weldability of Metals, API 577. There are entire books developed to the weldability of metals and alloys. Weldability is a complicated property that doesn't have a universally accepted definition. The term is widely interpreted by individual experience. The American Welding Society defines weldability as the capability of metal to be welded under fabrication conditions imposed into a specific suitably designed structure and to perform satisfactorily in the intended service. Weldability is related to many factors, including the following: the metallurgical compatibility of the metal or alloy being welded, which is related to the chemical composition and microstructure of the metal or alloy, and the weld filler metal used. The specific welding processes being used to join the metal. Mechanical properties of metal such as strength, ductility, and toughness. The ability of the metal to be welded such that the completed weld has sound mechanical properties. Weld joint design. Metallurgy and weldability. Primary factor of affecting the weldability of metals and alloys is their chemical composition. Chemical composition only control the range of mechanical properties in carbon alloy steels. It has the most influence on the effects of welding on the material. The metal is said to have good weldability if the limits are narrow. The metal is considered to have poor weldability. The heat cycle from welding effect produces a heat treatment of the metal that can have a noted earlier reached substantial effect on mechanical properties depending on the chemical composition of metal being welded. As noted earlier, each type of metal has welding procedure limits, and with sound weldment with satisfactory properties can be fabricated. These limits are wide, then good weldability. Let us see what is the limits. The carbon content of the carbon equivalent or carbon steel determines the necessity of preheat and post-weld heat treatment. One tool has been developed to help evaluate the weldability of carbon and alloy steel, and that is the carbon equivalent equation. The CE calculation theoretical is CE carbon equivalent is C plus Mn plus by 6, chromium, molybdenum, vanadium by 5, silicon, nickel, copper by 15. Typically, steels with C less than 0.35 require no preheat. Steels with C 0.35 to 0.55 usually require preheating, and the steels with C greater than 0.55 require both preheating and PWST. Weldability testing. One of the best means to determine weldability of metal combination of metal is to perform direct weldability testing. The simplest weldability tests are those that evaluate the strength and ductility of the weld. Tests that evaluate strength include weld tension test, shear strength, hardness, ductility, and fracture toughness test include bend test and impact test. Weld restraint cracking specimen are designed to permit a quantitative variation in restraint under realistic welding conditions so that the contribution to the base metal welding process can be evaluated with respect to contribution to cracking. Typically, weld restraint Test methods include the lay resistance test, slot test, rigid resistance cracking RC test, and circular weld resistance cracking test. Test methods that can use external loading include the implant test, tension test, resistance cracking, TRC test, and wear strength test, weld crack test. So lay test, slot test, taken test, RRC test, circular weld test. So many just names you have to remember. Externally loaded test. These are resistance test, externally loaded test, wear strength test, implant test, TRC test, lamellar tearing test, cantilever test, Cranfield test, underbead cracking test, longitudinal bead test, cruciform test, CTS test. So which is for what? Just see the thing. Austenitic stainless steels. Austenitic stainless steels are iron-based alloy that typically contain low carbon chromium between 15% to 32% and nickel between 8% to 37%. They are used for their corrosion resistance, resistance to high temperature degradation. Austenitic stainless steels are considered to have good weldability and can be welded using any common welding process or technique. The most important consideration to welding austenitic stainless steel are solidification cracking or cracking, distortion, maintaining corrosion resistance. The most common measure of weldability and susceptibility of hot cracking is the ferrite conmer of the weld metal. Austenite welds require a minimum amount of delta ferrite to resist cracking. The number of resources recommended minimum of 5% to 20% ferrite to prevent cracking. Distortion is more often the problem with welding of austenitic stainless steels than carbon or low alloy steels. Thermal conductivity of stainless steels is about 1/3 that of carbon steel, and coefficient of thermal expansion is about 30% greater. This means that distortion is greater on austenitic stainless steel than carbon steels. Most frequent tack welds may be necessary for stainless steels to limit shrinkage. Areas exposed to temperature between 800 degrees Fahrenheit, 1650 degrees Fahrenheit to 427 to 900 degrees centigrade for long enough time may precipitate chromium carbide at the grain boundaries. This causes a loss of corrosion. Loss of corrosion resistance due to chromium depletion. Using low carbon content stainless steel such as typical 304L, 316L or stabilized grade stainless steel such as 321, 327, 47 can prevent the phenomenon. It is also important to select the proper filler metal to prevent a loss in corrosion resistance. Low carbon electrodes or stabilized grades of bare filler metal should be used, and inert baking gas is needed. Nickel alloys such as alloy C276 and alloy 625 suffer from similar problems as austenitic stainless steels. Most nickel alloy material are considered to have less weldability than austenitic stainless steels. If some oscillations is not used, a high convex weld counter will result, which cause sidewall lack of fusion. Weld undercut or slag inclusion, the formation of slightly concave weld bit profile will more resistance to centering cracking. It is also important that bevel angle of the nickel alloys be wide enough to allow the necessary oscillation of the welding torch. The wider weld bevel will also be beneficial for the respect to weld penetration. Nickel alloys also suffer from shallower weld penetration as compared to carbon steel and austenitic stainless steel. To overcome this, the weld joint is modified by having the wider bevel and thinner root face. For the reason of preheating, which slows down the cooling rate, the weld is actually harmful as it permits more opportunity for hot tearing to occur. As with austenitic stainless steels, the weldability of nickel alloys can also be affected by presence of high levels, low melting point elements like sulfur, phosphorus, zinc, copper, lead. These contaminants can lead to cracking in either the weld or base metal. Hot tapping in service welding. API 2201 provides an in-depth review of deceptive aspects to the consideration when hot tapping or welding on an in-service piping or equipment. Prior to performing that work, a detailed written plan should be developed and reviewed. The following is brief summary of the welding related issues. Two primary concerns when on service welding on in-service piping and equipment are burn through and cracking. Burn through will occur if the unmelted area beneath the weld pool can no longer contain the pressure within the pipe or equipment. Weld cracking results when fast weld cooling rates produce a hard crack susceptible weld microstructure. Fast cooling rates can be caused by flowing contents inside the piping and equipment, which remove heat quickly. Hot tap and in-service welding operations should be carried out only with low hydrogen consumables and electrodes. Extra low hydrogen consumables such as EXXXXH4 should be used for welding carbon steels with carbon equivalent greater than 0.42% or where there is potential of hydrogen assisted cracking HAC such as cold workplaces, high strength and highly constant area. Cellulosic type electrodes E6010, E6011, E7010 may be used for root and hot pass. However, the manipulation of the low hydrogen electrode or root pass is not as easy, but it can be done by training and practice. It should be noted that cellulosic electrodes have the following adverse effect on the integrity of weldment. Deep penetration, therefore higher risk of burn through than low hydrogen electrodes. And high diffusible hydrogen, therefore higher risk of hydrogen assisted cracking. Flow rates. Under most conditions, it is desirable to maintain some product flow inside any material being welded. This helps to dissipate the heat and to limit the metal temperature during the welding operation, thereby reducing the risk of burn through. Liquid flow rates in piping should be between 1.3 foot per second and 4 foot per second, 4 meter, 0.4 meter per second and 1.3 meter per second. The faster liquid flow rates may cool the weld area too quickly and thereby cause hard zones that are susceptible to weld cracking. Low roughness properties in the weldment. Because of this is not a problem when the pipe contains gases. There is no need to specify the maximum velocity. The normal flow of liquids exceeds the values If the flow cools the metal below dew point, it is advisable to compensate by preheating the weld area to at least 70 degrees Fahrenheit and maintaining the temperature until the weld has been completed. High liquid flow may cause rapid cooling of the weld area during welding, creating the hard zones susceptible to cracking. Under these circumstances, the minimum interpass temperature may not be attainable, resulting in undesirable material properties. A flare line should not be attempted unless it has been confirmed that no explosive or flammable mixture will be generated during the welding operation. In this respect, it should be confirmed that no ingress of oxygen in the line is possible. In case where this requirement cannot be met, inert gas or nitrogen purging is recommended. The minimum flow rate of 1.3 feet per second, 0.4 meter per second of liquid and gas for liquids, and maximum flow rate is usually required. In general, 4 foot per second, 8.4 foot per second, 12 meter, 1.2 meter per second is upper limit. There is no restriction on maximum velocity of gas lines subjected to maintaining preheat temperature. Burn through. To avoid overheating and burn through, the welding procedure specifications should be based on experience of performing welding operation and similar piping or equipment or is based on heat transfer analysis. Many users establish procedures detailing when the actual thickness of the material to be welded less than 1.1 by 4 inch. The mock-up coupon represent the actual material in thickness. The welding parameters are recorded and the weld penetration is verified by etching. This information becomes the supplemental to repair package. The minima is bound through the first weld pass to equipment or piping less than 1 by 4 inch, 6.35 millimeter thick should be made with 3 by 32 inch, 4.76 mm or smaller diameter welding electrodes to limit heat input. Hot taps recommended when attaching a nozzle to pipe fabricated from plate material to prevent lamellar tearing of the pipe. Lack of fusion with GMAWS welding short circuit. Due to this inherent nature of the welding process, the VVP Code Section 9 restrict their process by requiring welders qualify with mechanical testing rather than by radiographic examination. Limiting the base metal thickness qualified by procedure is 1.1 times the test coupon thickness for coupons less than half inch thick, 12.7 mm per variable QW403-10. Limiting the deposited weld metal thickness qualified by the procedure 1.1 times the deposited thickness for coupons less than 12.7 mm or half inch thick variable QW400-432, making variables QW409.2 an essential variable when qualifying a welder for GMAWS process. The quick freeze characteristic which can result in null is the reason this process is frequently written out of purchase requisition and the inspection is required in pipeline welding. Automated ultrasonic has been adapted to overcome this problem. The risk of LOF associated with GMAWS means restrictions on qualification of welders using radiography only. The inspector should make note this potential problem. Caustic service. Carbon steel and low alloy steels are subjected to stress corrosion cracking and in caustic service. Austenitic type 300 series stainless steels can be sensitive to caustic cracking in high temperature steam environment. Weld joint nomenclature, electrode identification. There are 5 types of joint, that is butt joint, corner joint, T-joint, lap joint, and edge joint. A total 5 types. Joint type and applicable welds. So this is the nomenclature for welding. Square butt, scarf butt, V butt, bevel butt, U, that is U group, J group, flare bevel. Is the fillet, plug, stud, spot, seam, bake up the bake or baking, surfacing, flange, edge and corner. The reference line is shown dashed or illustrative purpose. Systems for various weld joints. Weld all around, field weld. There is a flag. All around is a circular. This circle melt through is something like this. Congeable insert square. Baking or spacer rectangle. Flush or flat. Convex or concave. Supplementary symbols for welds. So this is the weld symbol. How elements in the area remains as shown when the tail and arrow are reversed. So anything reverse, no problem for AWS. So this is the arrow side and this is the arrow side, this is other side. If anything above is other side, arrow side should be in bottom. The arrow is pointing that side, written on the bottom. The far side or other side is written on the top. One to see what is there. Finish symbol, two counter symbol, groove weld size, depth of the weld size and strength of certain welds. So this is 3, 4. 3 is the bracketed and 4 is outside. So groove weld size and depth of bevel size or strength of the center weld. Certain weld. 5 specification process, other references. Everything should be in the tail omitted when reference is not used. So 6, 7 in the tail. 7 can be upside and downside, no problem. Eight is the groove angle, included angle of countersink of plug welds. So this is 8, then 9, 10, 11. Eight is the groove angle, included angle of the countersink for the plug welds, root opening depth, filling or plug and slot welds, length of the weld, pitch. So pitch is outside is the length, and then pitch, LP, length LP. Field weld symbol already shown, weld all around symbol. Arrow containing reference line, arrow side member of the joint, arrow side joint. Reference line, number of spot seam, stud, plug, slot or projected welds. Reference line, the center line. So this one is the reference line. So this is how marking root opening, root face. This is the root opening, this is the root face 2, and 3 is the groove face. Then 4 is the bevel angle total, and the half bevel angle, included angle or groove angle is 5. 6 is the groove weld size. Plate thickness is T. Groove weld nomenclature is the SMW welding electrode identification system E. 60 is the strength, 70 is strength, 70,000, 60,000 position, and the coating operating characteristics. ER is for electrode rod. Here is the strength 70, 60 S solid wear, and then chemical composition 2, 2, 3, 4, 9, something like that. FCW welding, electrode apply identification system. Electrode, this is the strength, position, chemical composition, operating characteristics, FAW welding electrode identification system. EGW welding electrode is not required. Actions address the improperly made production welds made by an unqualified welder or improper welding procedure should be addressed to assure the final weldment meet the service requirement. Welder may be unqualified for several reasons, including expired qualification, not qualified for thickness, not qualified for the technique, or not qualified for the material of constraint. Identify and quarantine all weldments made by welder. Test welder, pass and fail. If fail, apply retest criteria. Test welder, fail, cut out welds, all joints cut out. Then pass. Okay, consider ND for QAQC, accept the documented welds. Potential causes: qualification, expired, not qualified, and range, not qualified. In method, not qualified. In material, suggested action for weld made by incorrect welder. A review requirement: fail, cut out and reweld with correct WPS figure. Hold, determine properties of WPS figure. A review of rerun picker. A review or rerun picker unsuitable for application. Cut out and reweld with correct WPS figure suitable for application. Repair weld incomplete. If fail, repair weld incomplete and if pass, review and pass, accept and document welds. Steps to address production welds made by an improper welding procedure. Here there is a radiography report, Annex C, example report of RT results. You can follow. That's all. 577 finished. We'll stop here.